Saxon Advanced Mathematics, Lesson 18, Part 2. Sorry, you guys, if I don't put my phone in airplane mode when I'm recording lessons, then if somebody reaches out to me, it sometimes bumps my phone off the video, and I'm merrily teaching away, and it isn't till later that I realize, oh, it actually stopped recording. So here, I believe, is where we were at. We had set up our two equations involving the digits in the tens place and the ones place, and then the values of the actual numbers. What we do next, our strategy we see is we're going to rearrange this A equation so that we can substitute it. We could subtract the T or the U. I tend to leave the first variable and subtract the second. That's what I did here. So I have T equals 5 minus U. I'm going to substitute that into this equation, but first I'm going to just use algebra to clean up this equation because I've got U's and T's on both sides. So I'm going to I'm going to subtract 10T and I'm going to subtract a U. So there's me doing that. And then I will clean up and get a new version of equation B, 9U minus 9T equals 9. And then I say, wow, look at all those 9s. Let's just divide everything by 9. And that gives us a much cleaner, this is our equation B. New and improved, wouldn't you say? Okay, so now I've got this ready to go in here, so I'm going to put parentheses around my T, and I'll rewrite that value in there. U minus 5 minus U equals 1. And now I'm going to clean up those signs. U minus 5 plus U equals 1. I accidentally wrote a 2 there, just because. Okay, now I can add these like terms and add 5 to both sides, right? And I get 2U equals 6. Let's say I got this first, right? Those cancel. 2U equals 6. Divide both sides by 2. And I get that U equals 3. Okay, that tells me that the digit in the units place of my original number was 3. And then I know that the two digits have to add up to 5, so that makes it real easy to see that the digit in the tens place must be 2. This is a lovely answer, but what I'm really looking for is you to write this. Original number is 23, which is, John asked, what is the original number? If we were in a testing situation and you gave me this, I would accept that. I would give you full points for that. But I do really want to see this. All right? These are a sly little type of problem because you have to be able to manipulate the digits by their place value as we did right here. That's the secret to getting these problems right. Okay, that is 18.4. We are past the halfway mark. We're now ready to tackle a couple chemical mixture problems. Some of my favorites. Example 18.5. Remember that last year when we studied these, we called one a type A and one a type B. They might have been type 1 and type 2, actually, now that I think about it. But we had two types. I'm going to call them 1 and 2. And we're going to do one of each. So let me remind you of how they work. In the type A problems, those are the pour and dump kind. So in these, we have two, it's this weird sort of semi-smiley face thing, right? We have something in one, and we have something in another. Normally, these are all the same chemical, but these are different strengths. And then what we're doing is we're pouring them together in some combination to make a different percentage strength, right? And we write the amounts down here, and we write the percentages in the water. That's just how I do it, sorry. So this is what John tells us in 18.5. To get 1,000 gallons of a mixture, so we want 1,000 gallons, that was 56% alcohol. It was necessary to mix a quantity of 20% alcohol with a quantity of 80% alcohol. Notice that all of these percents are about alcohol. We don't know what the alcohol's mixed with, but in all these cases, we're talking about alcohol. How much of each was required? So what we can do is say this is what we poured and this is what we dumped. All right? Now, first we're going to write a quantity statement. The amount that we poured plus the amount that we dumped, two words for the same thing. It just helps us distinguish between the two strengths. Has got to add up to 1,000 gallons. Make sense? Now we write a value statement, and that's going to take into account these percentages. So 0.2 is the strength of what we're pouring, plus 0.8, which is the amount that we're dumping, equals 0.56 times the 1,000 that we know we have to end up with. These amounts are mysteries. Okay, so now we have two equations, we have two unknowns, we're good to go. So I want to do two things to clean this up before we start solving this. Let's call this A and B. In A, I want to solve this for one or the other of the variables so that we can substitute it in. You know what I like to do. I like to subtract the second one, so it's going to be P equals 1,000 minus D. Sorry, I'm squeezing in right there. And this one, I want to destroy these decimals because I'm not a fan. So let's see, I see this has 1 decimal place, 2. So I'm going to bump it twice, so that's going to be 20. That's going to be 80, and that's going to be 56. All right, so let's rewrite this one. 20p plus 80d equals 56,000. Okay, that's an 80. Sorry, it looks like 2 Ds. All right. Now we're ready to substitute this in right here. So I'm going to take that equation and just rewrite it before the plug-in. Sometimes that helps me not confused. I'm substituting for P, so where the P variable is, I just put a bracket, but I copy all the rest of this first so that I don't get crazy up in here. Here, I'm going to put 1,000 minus D, because that's the value for that P. Now I will distribute. Okay, that's just a distribution there. And I'm going to, let's see, I can combine these like terms and then I can subtract 20,000 from both sides. This cancels. This becomes 60D equals 36,000. Divide both sides by 60. We can divide by 10 to get rid of one of those zeros. 6 into 36 goes 6 times, and then we have 2 zeros left. So it looks like the amount that we dump in equals 600 gallons is our unit. Okay? So that's the amount of the 80%. I don't have to write that in my answer because my diagram clearly defines that the D variable represents the 80% solution. So I can say that the D equals 600 gallons, and then I know it has to equal 1,000 gallons in all. So the amount that we pour in must be 400 gallons. I can do that in my head. What I like to do, there's my answer. What I like to do is just add those to show that they add up to that and that makes sense. That's a shorthand way of showing my work that helps anyone who would be looking at my work understand, oh, I did check to make sure that P plus D equals 1,000. This is correct. Thank goodness, right? And that is, yeah, I'm just looking to make sure I got those right. That is the type A style of chemical mixture. And these are typically used when we're taking two different concentrations of the same element or solvent or whatever word you want to put to it, compound, and we're combining them to create a new percentage that's in between those two. That's what type A is good for. Type B is what we use in our next example. We're getting near the end, you guys. Hang in there. 18.6. And this is, have I been saying B or... I called it a type A. I don't know if it's letters or numbers, you guys, but I'm going with letters. Okay, this is a different scenario. This is where we start with something, and then depending on the story, we either add or subtract something else, and then that leaves us with a change. This is the change that we introduce in the problem, and that can take a variety of shapes. Sometimes we're evaporating, and that means we're subtracting out water. Sometimes we're adding butter fat to milk. Remember that problem from last year? It's one of my favorites. This can be 100%, or sometimes we're just adding a stronger strength of something. So this has to be fine-tuned in order to fit our story, but this is the basic shape of our problem, as opposed to last time where we had that plus that, pour and dump, boo, boo, boo. Okay, so this is our type B. And that's what we're going to use for this problem. How many liters of 64% glycol? So that's what we're going to do here. We're going to have 64% glycol. I don't know why I wrote it up like that. Here, let's make our bin bigger. Must be added to 77 liters of a 23% glycol. Put the water in it. Put the water in this one too. In order to get a 42% glycol. All right, so what we're doing here is we're adding glycol. So, again, we can start by writing a quantity statement, although in type B's, there's a funny little trick to this. The original amount plus the amount of glycol added will equal the new amount, which is going to be 77 plus G. Okay, this looks like it's nonsense, doesn't it? Because this plus this equals this plus this. How is that helpful? But it's helpful in building our next statement, which is going to be 0.23 times the 77 liters plus 0.64 times this mystery number equals 0.42 times the combined. So you can see that setting up this isn't a separate equation that we have to solve, but it helps us prepare to do this work properly, because we can see, oh, these are the quantities, and now we have to multiply each one by the strength or the value, right, of the glycol solution. I'm just double checking to make sure we're right here. John asks us to be careful in using G for this because he wants us to remember that we're not adding straight glycol. It's 64% strength. If it was straight glycol, we would write 1.00. But in this case, it's not. So he asks us just to be careful and remember that this is actually a glycol solution. Glycol, I looked it up once. I didn't remember from my chemistry days. Glycol is a chemical that's often used as an additive to other chemicals. So for what it's worth, it's just a chemical. It doesn't matter. All right, so we wrote a quantity statement. We don't need to solve this as a system because we only have one variable, but we use this as a base to build this more complex equation, and then we can solve this for G. It's the only variable we have, though we have it in two places. All right, John recommends that we use a calculator on this because the numbers are not going to come out real cleanly. So if you've got a calculator handy, grab it and run these numbers through as I write them down. My calculator's busy filming. So I'm going to say that this should multiply out to 17.71 plus, we know this is right, 0.64g equals, and then this, once we distribute and multiply, it will be 32.34 plus 0.42. Ooh, I ran out of space. Let me squeeze. 0.42g, which we know is right. We distributed there. Okay, we subtract the 17 and we subtract the 0.42g. Cancel, cancel, we get 0.22g equals 14.63. And then we divide both sides by 0.22. And you should get that the amount of glucose that you need to add here, I like to circle that we're adding it to, just to clarify, is 66.5 liters. And that's our final answer. Okay. How do you know when you're allowed to use a calculator? One big hint is that the answer is in decimal form. If you are working through and you get to say this point and you see all of these decimals and numbers that do not look like they're going to come out, it's okay if you take a peek in the solutions manual just to see how messy the answer is. If you get an answer like this with a decimal in it, grab your calculator and go for it. I do not like us to use our calculators often or automatically because it makes our brains very lazy, and it happens very quickly that we lose our sharp edge on long division and multiplication. So I'm careful not to overuse, but on the other hand, we're getting into some really complex calculations, and in a chemistry class, you would be using your calculator to solve those. So I want you to have a little bit of comfort with that as well. So if it's a messy answer, go ahead and use it. If the answer here was G equals 80 liters, I would say no, you can do that by hand. Don't use a calculator. All right, so that is the type B diagram where we're introducing change into a system. Type B only has one variable. The type A's have two variables. That makes our strategies for solving them different, okay? Please make notes in your binder cover to remind yourself of what you need to know to solve these two types of problems. They're tricky. This is tricky stuff, you guys. And then the last example is also from the world of chemistry. The weight of the carbon in the container of recipe for a compound molecule. Whoops. Check and make sure I didn't bump myself too far. All right, here I am down here. The weight of the carbon in the container of that was 113 grams. What was the total weight of the compound? And then John gives us the atomic weights of the different atoms that make up this molecule. This is essentially a ratio problem, so we're going to set it up as I set up my ratio problems. And it looks like this. We're going to write the name of the compounds here. Then we're going to write the ratio of the atoms in one molecule of whatever this compound is. Then we're going to multiply it by the weight of each one. This is getting kind of sciencey. let me just give you a basic explanation. Atoms are the building blocks. Molecules are the recipes that the atoms take when they're combined with others. This particular recipe I'm going to write down is C3H7Cl. This is a recipe for a compound. If I remember properly, it's carbon, hydrogen, and chlorine maybe. But I can just write the letters here. I don't have to understand them. Then I need to have a total row as well. Okay, so this is the recipe. These are the ingredients. This tells me how many atoms of each go into this compound. So it's 3 to 7 to 1. The weight of each raw ingredient is given in the problem. Right here. You're not expected to know that. Those are the weights of each atom of those of the ingredients. So we write those down. 12, 1, and 35. Okay? So if we have 3 bunches of carbon and each one weighs 12, then the total amount of carbon in one molecule of this is 36. Hydrogen, the recipe calls for 7 atoms of hydrogen. They each weigh just 1. What is the measurement here? Grams. Okay. And so that would be 7. We're multiplying these, right? 1 atom of chlorine times 35. That one's a chubby, right? So the weight of the compound or molecule, John uses the word compound, which simplifies things from a chemistry point of view. So we'll talk about the compound weight rather than the molecular weight. We add all of these together to find the total weight of the molecule. So that would be 71, 78. Okay, we don't need these total spaces. Now, all of this is just to find the basic ratio of the weight. Now we need to know the actual weight of our compound. Okay, this is the weight of just one basic unit of this, but I think we have more than that. Let's see what John says. The weight of the carbon in the container of this was 113. So the carbon was actually 113. What was the weight of the compound? And that we mean the total. Okay, so this is just a fancy ratio problem, and what we want to do is use these 2 numbers and these 2 to set up our ratio. So what we say is if in a single unit, a single molecule of this compound, carbon represents 36 of the total 78 grams, but we actually have 113 grams of carbon. So what would the total weight of our compound be? That's the way we set this up. And now all we need to do is solve. So we're going to go cross multiply. 36 times x equals 113 times 78. Before we multiply this, we're going to divide. This is just a hot mess, so you can use your calculator here to get that x equals 244.83 grams. That would be the weight of the compound if your carbon was weighing in at 113. And we use this ratio of one single molecule of the compound to set up the ratios. Okay? Hopefully this is a reminder. When I talk to you this week in our video chat, I'm going to ask you about all of these word problems. This was a really tough lesson, you guys. It covered so much ground, and it covered not only a lot of different styles, but like the hardest variations of these problems too. This was rough. So breathe, relax, and talk to me when we video chat and let me know which of these are working for you, which aren't. I'm going to be asking you if there are problems that you struggled with, and I want you to have ideas if there are, problems in the homework that are making you crazy. Then that will be our time to really go over that. Okay? So make notes, and by all means, you don't have to wait for the video chat. If you're feeling overwhelmed, shoot me a text, and we can talk about it while you're doing your homework. Great job. If you're still alive, if you're still breathing, if you haven't crawled under your bed and whimpered and told your mom you don't want to grow up, you just want to be a kid forever, I'd say you're ahead of the game at this point. So congratulations. If you're still listening, I'm done. Thank you. Goodbye.